So what I want to do today is to give you guys kind of an overview of what we're doing on the mitral valve about the last 4 or 5 years. We've been working on heart valves for about, since the early 90s. And for those of you who are mentors to undergraduates, my first exposure to the valve was actually as a master's student working on some work. It was actually quite interesting. What we're talking primarily about is about the mitral valve here. Now, there are 4 valves of the heart. The mitral is one of the so-called atrioventricular valves, and you can just see basically that the aortic valve is 3 leaflets, and it's a high-pressure, high-flow valve, whereas the atrioventricular valves are low-pressure but high-flow. And the mitral valve really is not an independent structure. The aortic valve is kind of a little bit more so, but it's integrally connected to in a functional part of the left ventricle through the papillary projections and also the chordae. It's a bileaflet valve. It's the only one that there is. Has the largest orifice area. It bears at least 100 millimeters of transabdominal pressure, usually quite a bit more than that. And the thing that's really interesting is at least 100,000 times a day. And as one of my old physiology teachers used to say, if it didn't, it would be inconsistent with life. I always like that. Now, what's the real problem? The real problem, there are multiple types of mitral valve disease. The big one is what's called ischemic mitral regurgitation. And that's actually not a disease of the valve, it's a disease of the ventricle. And what happens is that portions of the ventricle will dilate because of infarction. This is for those who are not familiar with it. If there's a coronary blockage, portions of the heart wall will die because of insufficient blood flow, and it causes the wall to dilate outward, and the valve no longer collapse. Now, this in and of itself may not sound so terrible, but in addition to regurgitation into the left atrium, you can actually have many problems, including congestive heart failure because of the vascular fluid. You can cause the regurgitated chest can cause thrombi to form. You can get stroke and many other issues. So it's not something that you want. There's quite a bit of it, at least 300,000 cases per year in the U.S. alone, and it's characterized, if you don't operate, by an extremely high mortality rate. So the cure for this, or the treatment, I should say, is really very simple. You put a ring in there. It's called an annuloplastic ring. And this was developed by a fellow, very famous French surgeon called Chordae, a hard one to get out. Anyway, he developed this ring idea, and the idea is that it reapproximates the valve and through an undersized annulus and causes it to recede. Now, if you look at the before and after flow, you see here the flow of the virgin jet going up after the post-repair. Looks pretty good, so we're fine, right? Everything's all hunky-dory. Well, no, very poor long-term outcomes, often as much as 40 to 50% within 2 years after surgery, sometimes even more. So over the years, various manufacturers have come up with all kinds of different ring designs, ones that can be better or worse. And of course, none of this is based on anything other than just various rather arbitrary designs. So part of the problem is how much of this repair durability is due to the design of the ring versus other factors. Now, we are not the first one by any means to develop computational models of the mitral valve. This has been a very active area from at least '93, and there's been a whole number of people doing this over the years in various ways. What we do, we think, is actually quite a bit different from what other people have done. Now, before I get into that, let me tell you some of the modeling challenges. One of the problems is that the valves move quickly, they have low mass, and they're in an anatomically inaccessible location. So that makes it very difficult to image. In fact, you can only image a leaflet. This is from the Visible Heart Lab, and one of the surgeons I collaborate with, when I asked him, what does the chordae look like when the valve opens? He said he doesn't know, he's never seen it. So at least give you some idea. And we actually showed that this is measured, you have put markers on the valve, and if this is when you're excised, black, red is when it's in vivo stretch, and blue is when it's fully loaded. So it undergoes fairly large deformations, and it can actually go under 30-40% strain from the in vitro reference configuration. One of the other big problems is anatomic variability. Anatomic variability, of course, for those of you who work with anything biological, is the name of the game. And this is just from different species, let alone within different hearts. So there's a whole bunch of structural variations that you have to deal with. So to summarize, you have the problems with regurgitation becoming more prevalent, pathological alterations in geometry, very controversial treatment options. Computational models are a very promising tool. Most of them and all the previous ones are largely oversimplified and often ad hoc. And above all, none have been shown to have any real predictive power yet. So in spite of many years of very concerted effort by some very talented people, we need to develop new models to be able to get around some of these challenges. So let's go back, and one of the first things we did, and this is in collaboration with the Ajit Yoganathan Laboratory, the Cardiovascular Fluid Mechanics Laboratory at Georgia Tech. This gives you an idea of in their heart simulator device. This is an O-line mitral valve, just the complexity of those chordae and leaflets, and these are the papillary attachments. And of course, this is not really a physiological prep, it's just meant to show it, but you can see what you're really dealing with. Then we would actually image a number of valves. Now, what we try to do is mount the valves and hold them in their system at an anatomically correct location, configuration, and you have to go through a number of trimming, and this actually takes quite a while to get this. Now, one of the things we did is we began to look at the anatomy of the mitral valve from a very quantitative point of view, and believe it or not, this has actually never been done, in spite of all the different and we looked at 5 mitral valves. These are the leaflets, and these are the chordae reconstructions. So try to get some idea of what the geometric shape of these are and what anatomical variation. And when we started this, the original idea was really very basic. Can we come up with some type of template or atlas of the mitral valve that we can put together and say, this is a representative mitral valve that we can use in patient-specific simulations? Seemed like a very simple thing to do, but it got really quite complicated. One of the challenges, for example, was dealing with things like branch structures. Now, this is very different from vascular structures, where there is some underlying physical principle, like the bronchial tube branches. Those of you who have ever heard of the Weibull distribution? Weibull distribution was developed by a guy named Weibull for the bronchial branches, and I actually met him when I was a graduate student. And he's the one who developed that branch tube structure, but it's all based on physiology and flow and transport. Similar things for branch blood vessels, but in the chordae, there's no such law that at least we know of. And so we began to really just look at it from a geometric going through the reconstructed branches. And there's even questions of what constitute, what's the chord, what's the transition zone, what's the leaflet. These are very arbitrary definitions. And we worked through a whole elaborate procedure to come up with a smooth reconstruction. And then we took these binary images and linearized them for modeling purposes and try to maintain, some semblance of a realistic cross-sectional area. Now, the biggest problem, at least up to this point, was how do you model the leaflet? Actually, it had not been done. And there's no set way to do this. So we went back to these families. This was very popular in the 90s, called superquadrics. And they were used over the years for representing a whole variety of anatomical shapes. And they're basically a ellipsoidal-like family. Ellipsoid is actually a degenerate form of the superquadric surface. And you can tune these, and the thing that really makes them so nice is that they can produce mitral valve-like shapes from relatively few numbers of parameters and are very tunable. So this gives you an idea how we develop the coordinate system. This peels it out. This is as you move around, and then you've actually, if you take that and peel it around, this is what the whole valve leaflets is: the anterior leaflet, posterior leaflet. This is the annulus, and this is the coaptation or free zone. And we can actually use this to begin to map this whole system. Now, we actually took these, we look at just the leaflets and look at these high-resolution CT data and use the superquadric as sort of a first cut, sort of like a DC level approximation. So there's rid of the surface. And the idea is that we want to break it up into a major kind of a DC level kind of approximation, and then the fine scale features are added onto that. You'll see why this becomes very important later. So when we did this, we actually went through a number of elaborate procedures to find the closest points, reconstruct the valve, basically use a variety of confining or constraining methods to obtain the final shape here. And then, so what we actually end up doing this on the ventricular type, for example, here's the superquadric shape. This is the 3D mesh, the superquadric shape. And then we have the difference field between the fitted superquadric and the actual ventricular surface. There's a side view of it, and there's the distance plot. And then for the atrial side, we did the same thing. And this allows us to now to create representations of both surfaces separately. But again, notice that we're using the superquadric to capture the overall shape of the valve. Now, when you peel that out, you actually want to take a look at this. One of the things we thought of is that, look, we can get the geometry. Well, one of the questions we had is how much information do you actually need to get faithful representations? You can actually reconstruct every molecule of that valve, but do you need all of that? So the question of what's the minimum practical resolution is a big issue. So one way we did that is to go back to these reconstructions, and one of the things that this superquadratic representation allowed us to do was to represent this as a 2D problem. And then from this, we can represent and say, okay, so what we really have is a height map, okay? And can we use Fourier methods to figure out, to lower the resolution levels? And we did this using what's called a non-uniform Fourier FFT, or NUFs. And we can actually create Fourier representations of both the ventricular and the atrial surfaces separately. And this gives you an example of what the reconstructions look like, and this is the point of difference, and actually it's quite high fidelity. This is everything that we need to get it. Okay, so we can say for each valve, we can now represent this analytically. And then the next thing we did was to add the Chordae to it. You can see here the green represents our approximation to the insertion. And that insertion zone, as I'll tell you in a little bit, actually turned out to be not only very important, but it's actually mechanically dominant. We thought the leaflets were the mechanically dominant, sort of are, but those insertion zones are really quite complex. And because of the way we reconstructed this, we used these fiducial points that were placed on the valve. The valve was pressurized, and then we use those to back open the valve, because you can get the highest fidelity reconstructions of the chordae from the closed state. And we use an inverse method to back out what those chordal structures have to be. So when the valve is fully loaded, it matches that. So it's a little bit of an inverse modeling trick to get that. So this is what the chords look like. It's just very hard to get this in there in the Georgia Tech particular system. Okay, so this is sort of the calibration, and just to elaborate what I was mentioning in the previous slide, we start with this slide. When it's loaded, we know that these fiducial points that are on the pathway muscles move upward. We know that the annulus moves upward because it's actually placed on a deformable ring mount, and then we can match these, and these become part of the boundary conditions we apply, including matching the displacement field by the marker. Now, one of the things that we're just looking at, and I don't want to get into too much detail on this, but this is a fibrous tissue, and I'll be talking more about the fibrous structure of the mitral valve a little bit later. But we wanted to say, we know that the fibers are arranged in some planar array, and we know they're made of undulated fibers. So we have two distributions. One is their planar distribution, and the other one is how much they recruit. That is how much, when the tissue gets loaded, how much those fibers get straightened out. And we integrated those together to come up with a single tensor index called chi, which basically says how much of structural reserve do you have left. So what it really means is, as the valve loads, the fibers straighten, they rotate, and at some point you've straightened all the fibers, and all the fibers are loaded. So when chi is the identity matrix, that means all the fibers in all directions are now bearing load. And fractions of that mean that you still have some structural reserve. And this actually turns out to be kind of a nice index to show you how all of this is actually working, how the fiber network is working. So don't try this at home. This is the whole pipeline. It took about 2 years to develop. And starting, and we thought it was easy. By the way, we said, oh, we'll do this in a few months, 5 valve, piece of cake. And it took a long time to just this whole pipeline to get from this to this. Okay, and calibrated and validated, and a lot of interesting things that we learned about it. Okay, now this is kind of the final outcome. You do all this stuff. What do you get? Well, 5 valves. This is the original geometry, and then we can break back the level of resolution by this Fourier method I was mentioning earlier, and we can figure out how much resolution you need. Now, what's the importance of this? Is very important because in vivo, if you're getting from human data, you only really can get something probably about like this. So we wanted to see how far are we off if we are approximating this down, and try to do this in a more systematic way rather than just going in there with brute force and saying this is what you can get, and so be it. And then we looked at a number of different resolution levels, looked at the strain in the circumferential direction, and there's the amount of fibers that are recruited. Notice most of the fibers are recruited in the central belly, and even at this one, there's more to it, but there's a lot of loading here. The greatest strains are there, but generally speaking, not a lot of variation from about 2,600 elements to over 10,000 elements. So this resolution seems to work pretty well of an element size of about 1 millimeter, whereas this element size is about half that. So it's actually relatively insensitive. Once you get the minimum resolution you need, any further refinement really isn't necessary. Now, you can spend all day looking at plots of the mitral valve, and when you look like this, and just hundreds of these things that we generate. And we said, I told my staff, I said, we need to come up with a better way to compile this information. And we came with something called the composite analysis score, CAS, which is really nothing much more than a sum of the errors from the most accurate model, where every bell and whistle we've measured is put in there, to the simplest model, which is a very crude one. And we come up with a score where score 1 means it's equivalent accuracy to the Uber model, or the the ground truth model. Now, the ground truth model takes about 90 minutes to run. These are 3 different states, which I'll talk about in a little bit. Normal, dilated, and repaired, and I'll talk a little bit later what that means. But if you just focus on the overall value, as you decrease the fidelity of the model, you actually see a substantial compromise in the quality of the results. So if it's a very low resolution model, even though it does it in only about 15 minutes, you really compromise by over double the amount of quality of the fit that you get. So a good compromise seems to be medium one of these 2 models. They take about the same length of time, but the medium 2 model, which takes about 1/3 the time, gets you nearly the same level of quality in terms of the results. So this means this is the model of choice that you want to use, and this is all you need. You shouldn't do less, but you don't need more either. And believe it or not, you don't see too much of this in the biomechanics modeling literature, and it's actually very useful to know what your resolution limits are. Now, one of the other things we did is we looked at things like material model, like how accurate, and I think those of several people like Alan Eberhard and Joe Berry know that I spent way too much of my career worrying about constitutive models and material models of tissues and all this really cool stuff. And it turns out that for the mitral valve, we did the whole full map, the collagen structure map, and very accurate structural models, multi-layers, all this shtick. And you know what? You don't need it. Not for the organ level. You do need it if you want to get down to cell level simulations, but for the organ level simulations, a simple isotropic model is all you need. But the model has to be nonlinear. Now, why is that? That's because we go back to these guys. These guys, those insertions, all of that infrastructure, superstructure, or what's called the subvalvular apparatus, is acting altogether collectively as an isotropic material. So the leaflets themselves, if you can isolate those from the insertions, are anisotropic, but that collective structure of the insertion really acts structurally as an ideally isotropic, but the nonlinearity you have to capture exactly. Why? Because the leaflet has to be able to stretch up, co-op, and then lock up. You have to capture that behavior. It's another interesting insight from doing model. Okay, so everything I've showed you up to now is great. We've got these high-resolution models. We can work out different ways to get the structure recalibrated. But this is dead tissue sitting in somebody's tank on a research lab. What about a real mitral valve? Okay, well, it turns out that you can get, these days, using transesophageal echo. Now, as I mentioned to you earlier, one of the challenges in getting working with mitral valves is that they're very difficult to image. CT, MR don't do a very good job. The state of the art is transesophageal echo. For those of you who don't know what that is, that's where you swallow a probe and you move it down and they actually can 3D reconstruct the valve. You can get the leaflets pretty good. I don't know about you, but I don't see any chordae there. Okay, they're gone. So you can get the leaflets very nicely, open and closed, but you can't get the chordae, and I'll talk about that problem in a little bit. Once you get the leaflets, you go through this rather interesting pipeline that my student Bruno Rigo developed to actually reconstruct the entire valve. It does a very nice job. This is from an ovine sheet, but we can do the same thing in human, and actually the human data is even better than the sheet because of the size of it. So we can get the leaflets reasonably well. We can get the whole leaflet pretty good in the fully open configuration, not in the closed, but we have ways of getting around that. Now, how do you add the chords? You can't visualize them. What do you do? Well, we looked at as we said earlier, we actually did a very elaborate study that came out last year on the chords. And actually, this is my first contribution to gross anatomy. I think I should have found something new in gross anatomy. which nobody ever actually quantified these before. And we actually looked at these in branches and branch patterns and tried to see if there's something consistent in them. And as an overall population, depending on the various metrics like the length of the branches, the non-planarity, and various metrics we won't get into, cross-sectional area, as a population there is some general trends, but individually it's not. And we were thinking that even if this doesn't work out, we can use this to get into the candelabra manufacturing business. But that really wasn't going to work. Okay, so this idea of creating this patient average model, you can do it, and there is whole theories of what's called arborization models, where you can generate trees. Those of you who ever play those flight simulator games to see what the trees look like, there are people who do those. That's how they generate these. It doesn't work. So we went back and said, okay, let's take an approach similar to what we did for the leaflets. Is there something we can do and develop what's called a mechanically equivalent network? And so this is what they actually look like, and you can see it's a very elaborate structure. And we looked at things like cross-sectional area, branching patterns, distributions of origins, distributions of insertions. And then we actually came up with these models where this is some of the full-blown model and various levels of simplifications, and actually looking at ways. And you can see this a little bit better. If I took, these are the insertions, and if I plotted those over that same plot that you showed before, you can actually break these up by, this is a uniform grid, this is within the elements, and the red represents one property of muscle and the blue represents the other. So we have some anatomic cues, but otherwise that's fairly randomly placed. We can then do the same thing, but make it increasingly less dense into very sparse. And then we went back and said, okay, we know that, for example, the major strut chordae are here. These are the marginal chords that insert here, and we can composite these together and get some flavor of the native anatomy. And when you put these all together, there's the native, and these are all the different simplifications we can end on down into the mitral valve. And we said, okay, what effect does this have on the accurate simulation? Again, for those of you who do modeling now, what's nice is that we have these high-resolution ground truth models that we can test all these things against. And what we found, and when we look at the valve leaflet stresses, is that they had some effect, but not that much. As long as you had it relatively distributed, fairly uniform, it actually was pretty good. And same thing for the radial strain, and then the same thing for the atrial surface collagen index. So there's some differences between them. It's interesting to see what they do. But overall, as you get a reasonable distribution, you can actually create a very accurate model for this. Okay. So what this means now is that we can actually take those in vivo 3D reconstructions, match them against, create these artificial chords, and be able to begin to work toward actual fitting as actual data. And we're working on that now. I think within a couple months we'll have some results to show where we can run this whole pipeline through completely in vivo generated data. So we're pretty close to it. The in vitro work has all been done and it's all been published. Okay. So I kind of promised a little bit about everything that I've mentioned to you is all organ level, it's all imaging based, it's all based on what you can visualize at an instant in time, either in a normal valve or in a pre-surgical scenario where you have a patient that needs to have the valve repair. But what's really going on is what's driving this valve remodeling down. And some of this reason for the fact that the valve repairs fail is also because the mitral valve itself remodels profoundly, and I'll talk about that in a bit. So one of the things we've looked at is alterations in mechanical properties of the geometry of the valve following infarction and also the tissue. Now you would think this would be very well known by now, and actually we were one of the first ones ever to study this. So we talked about the root problem is that these mitral valves grow and remodel following an infarction. In fact, it's not even really ever been known before. Now, from a surgical point of view, they're like, look, if you have a patient that has IMR and they're treated within a week after that to put the ring on, the valve is probably relatively unaffected. But sometimes they have to wait for months because of a variety of other clinical considerations. And during that time, there's going to be some very interesting modeling going on. So we went and we did this in a large animal model in the sheep, and after about 8 weeks, we went back and looked at the cross sections of the mitral valve. Noticed the very beautiful multi-layered structures, elastin and collagen, and so on. Did 3D reconstructions and determined the amount of collagen, glycosaminoglycans, and elastin depending on where you are here in the valve. So we did a very detailed study. And we also looked at what happens with annular dilation. And I want you to kind of keep this figure in your mind as we go on. This is what happens before MI. This is what happens, excuse me, after myocardial infarction. There's a very large increase in area, and that increase in area is what probably what makes it so lethal, and I'll tell you about that a little bit more in a minute. So you have, look at the annular length. This is pre-MI, so you can see the annular length really goes up quite a bit in open and closed states, and also the normal side area. So that valve really stretches out. Now, when we looked at the properties of the valve leaflet before and after 8 weeks, we found that there's a big decrease, in the radial directions. Not too much, a little bit of an increase in circumferential, huge decrease in the stiffness, increase in stiffness, and the area goes way down. So basically, that tissue becomes dramatically stiffer, and the leaflet itself really stretches out. So a lot of remodeling going on. So we take a look at what happens post-MI. Collagen goes up, gags go down, elastin stays about the same. But we see some actually very profound collagen remodeling, and this is usually because this central fibrosis layer becomes augmented. But when we look at the cells, it's very interesting. You look at what the cells are. Now, the cells within that population of little interstitial cells, you can see them here, and they populate and maintain the extracellular matrix. Turns out, on average, they seem to be more elongated. That's because the tissue is stretched out. And in fact, if you plot the nuclear aspect ratio versus the MR grade, this means more regurgitation, greater annular dilation, you see a nice linear increase. So basically, all this remodeling is driven by the impact it has on the shape and the loading on those composite cells. So the question, why does annular dilation that we observe, why does it have such a dramatic effect on the tissue? We try to get some insights into this. So we went back to our in vitro model, and we looked at the normal, repaired, and disease states. And these are actual annuli reconstructed from actual sheep that are subjected to this. And you can actually see, we also did parametric studies that we took the in vitro model, and we know approximately what the in vivo annulus is in the normal sheep, and we prescribed that. That's this guy here. And then we said, what happens if you shrink it down by 20% or increase it by 20%? So this is a basic parametric study. We also looked at the effects of the saddle, which is what happens in the native valve. And what we found is that, first of all, we went back to all 5 valves, okay? Look, this is this example of circumferential strain, and what I want to mention to you here is that this is the normal dilated repair. We calibrate the model here, but these two states are predicted based on only on the in vitro and in vivo information. So we see a fair amount of consistency, and I think you can see here a little bit more about what this actually does. Oops. And you can actually see, watch the actual collagen structure here, and then the stresses here. And you can see it actually regurgitate there. And as I was telling our friends at lunch today, the whole purpose of doing computational simulations is to generate cool movies. And you can actually see how the valve loads. Notice that high doming there, and that's part of what it gets. And this is really, this is normal. This is what happens when it's dilated. The annulus increase. It's just the stress on that system gets like quadrupled just by a 20% increase in diameter. It's not much to get it to do that.
So, Mike, the cords are passively elastic.
Yeah, they're just moving along. That's basically what they do approximately. That in the native valve, there's always some residual loading, but this is all calibrated, so we know they do the mechanically equivalent of what they're supposed to do. But the cords aren't really the issue; it's really the annulus. Now, often what happens, by the way, we're only imitating what happens in the annulus, which is the main effect, but there's also effects of the papillary muscle as moving passively in or moving out, because they often get pulled down because the ventricular wall is being dilated out. So what I'm actually showing here is probably an underestimate of what really goes on. So the short of it is, again, what we wanted to do is the surgeons like to break the valve because the native aorta has 3 leaflets. They like to do the same thing. There's like 1, 2, 3 anterior leaflet sections and 1, 2, 3 posterior leaflet sections. And again, there's that good old composite score. And so basically, the way you think about that is that this is a relative change in score. So 0 means it's no different from the normal case. So this is the in vivo base. This is the what happens when you dilate it, and this is when you bring it down by 20%. Well, what you notice here is that this is the normal, not a lot of difference. This represents about the average value of the normal. If you shrink it down by 20%, it doesn't really do a whole heck of a lot. But if you increase it just by 20%, look what happens. And so that really means that all these segments get very heavily overloaded. It's really driven by these stresses. And the A2 and the P2, these two center sections, really get it the worst, okay? And all we're doing is simply dilating that annulus. And this is part of the reason why that remodeling that I showed you before occurs, because it's all driven by the stress-induced remodeling, simply by a dilation of the annulus. So one of the things we looked at is there any other evidence in the literature. A couple years ago, we started this really cool study. One of my former postdocs, Sarah Wells, who's now an associate professor of biomedical engineering at Dalhousie University in Halifax, which, as she reminds me constantly every time I talk to her, has free health care. So we went back, and she grew up on a farm in London, Ontario, and she did a study a couple years ago where she looked at what happens to the mother's the maternal mitral valve during pregnancy. So what's pregnancy? It's just overload, right? So I don't know if you know this, but your cardiac output in a mother goes up by about twice, and it actually causes the mitral valve annulus to dilate and actually produce remodeling. So volume overload causes remodeling in the heart. In fact, Sarah always had this funny saying. She said, "Pregnancy is a disease." But she said that after she had her daughter, so I sort of stayed out of that. But anyway, leaflets are not pathologic. This is a totally normal case. There's no infarction. There's no pathology of the ventricle. There's no pathology of the valve. It's just a pure stress-driven remodeling state. And we want to see any idea what grows. And so we know that, for example, pregnancy is a 40% increase in blood volume, 50% in cardiac output, 52% increase in LV mass, 30% increase in volume, and this is the price mammals have paid over the millennia for not laying eggs and getting that little bit of evolutionary bump, but it does have its price. And so we looked at conception, really early pregnancy, mid, and then term. All right. So what did she find? Well, she did these biaxial studies, and if you just plot the area, which is the product of the two stretches, just the area change versus the membrane tension, which is applied equally in both directions, you find that in non-pregnant, you get this nice nonlinear relation. If early pregnancy becomes dramatically stiffer, now that is not so much, that's very consistent with what we saw with the infarction. Well, what's really cool, it goes back. And I'm like, what is going on there? Okay. So this means there's some ability in this scenario for the valve to heal itself. It's the first time it's ever actually been reported. We don't know anything about how valve tissue remodels and repairs, okay? So we went back, and a little piece of advice for those of you who do wet lab work, always save your histology. Never throw anything out, and keep it clearly labeled, and put it someplace where it can be found, but not too easily. Okay. So we went back, and I said, let's look at the cell aspect ratios based on what I showed you before, and look what happens. Early pregnancy, see how straightened out that collagen is? And late pregnancy, it's returned back to its highly undulated state. Let me tell you, though, the leaflet is not retracting back. The leaflet area is the same. The thickness has not changed, but the thickness of the fibrosis, the dense collagen, has gone up. And we found the nuclear aspect ratio goes up and it goes down. And then we did some simulations of this, and we found that there was an actual net increase in the cell aspect ratio as you load it. So here's kind of the grand unified field theory for mitral valve remodeling. So the valve leaflet boundary conditions are altered. First, there's a stretching out, what like a permanent set. Fiber crimp is lost. And then over time, so you kind of go from here to here. Now, the cells don't like to be in this state. They're in, and I'll show you, there's some evidence to indicate that they become hypersynthetic in that state. And they want to go back to their homeostatic state, but they can't remodel the whole leaflet because the heart is still dilated. So what we think they are able to do is either secrete collagen along the fiber or in parallel. and it returns the fibrocrim back, although the net length of the whole tissue is still maintained. So it's a very peculiar form of remodeling. And so again, and if you can do that, you can actually get back to and return the whole system back to that level. So what we think is going on in the infarct case is that you've gone beyond what this system can handle. So there is some ability for that valve leaflet to remodel itself. But in infarction, if it's prolonged, you go beyond it and you get this really deleterious effect. So we get down to the cell level, and again, this is my multi-scale modeling shtick slide. So we're doing everything all the way up and down this pipeline. Get down to what's going on into the cells. Now, this is a beautiful micrograph done by Salma Ayub, one of my PhD students. And Salma actually, you can see the ventricularis, the fibrosa, spongiosa, atrialis. So when you get down to the microscale, it's not just a simple atrophic material. And if you look at the fibrosa, you can tell that layer has one function only, and that's bearing stress, and it's very tight. But within that are these interstitial, microvalve interstitial cells, as you can see here. Okay, and they're the ones that regulate and maintain this mass. Now, those of you who don't know, myofibril is a type of it's a mechanocyte. When activated, they will secrete collagen, and they become very highly upregulated in alpha smooth muscle actin. You can see some examples here. So this is a micrograph, a movie we did just recently, a paper we just submitted, where we wanted to get down to get an idea what the microenvironment of the mitral valve cell, the mitral valve was. There's your elastin. This is using focused ion beam scanning electron microscopy. Different collagen fiber bundles. Those are the fibrils. Okay, so those you know the difference between a fiber and a fibril. Whenever it was explained to me, never could figure out what it was. These are elastins. So elastin is not really quite fibrous, and it's not really quite struts. It's kind of a weird structure. And this is what the cells see. This is what the cells are sensing. They're living in this environment. So you can really get a sense of where they're going. So we developed over the last couple of years, Chung-Hao Lee, who's one of my former postdocs, he's an assistant professor now at University of Oklahoma. And when he's working now, he did this downscale model where we actually developed on all this micromorphology, a very precise model of the density. And this is about what the density of the cell. So the tissue, mitral valve tissue, is actually fairly cellular. It's about 10% by volume. And we can go back and we can do an upscale model and match it against these this is just sonomicrometry crystal. They're implanted on the surface of the mitral valve, and then we can record the leadings. And we were actually the very first ones that ever measured the strain in the beating, living mitral valve. So, and this was back done in 2006. So those of you interested in biomechanics, still a lot of really basic stuff you don't know. That is, if we can build this into a single model. And then we actually took this model, calibrated against from another study that we did, where we actually measured the nuclear aspect ratio as you apply biaxial loading under physiological levels, and using a 37-cell model, which was a pretty good representative RVE, and you can get that here. So we can actually map that, and we use a second St. Bernard-Kirchhoff model, which is a very, very simple model, actually, but it nails it really well. Gives you a modulus of about 5 kilopascals. And I think, there we go. So this is what the simulation shows, what the cells undergo in vivo within this RVE, using measured strains as a boundary condition. So, and they actually they get deformed quite a bit. So there's quite a bit of stimulation going on. So when these tissues deform, they really deform. And then we actually went back and looked at how that model compares between data from each of the 4 major layers that I was showing you before. And it actually just nails it. And what's interesting is that even though the responses in the layers are very different, the effective modulus of individual cells are surprisingly similar. And we think what this suggests is that the cells in the different layers are phenotypically very similar, but they are under very different loading because of the extracellular matrix composition and structure differences. And I don't think we have it here. So they may be phenotypically similar, but those of you may be wondering how sensitive that model is. I can send you the paper. We did all these sort of verification studies. And you need the second, believe it or not, you need the second, this St. Bernard-Kirchhoff material model, and that modulus to match that data is actually really quite sensitive to it. Okay, so what does this have to do with surgery? And so we wanted to go back, and we went back to some additional sonomicrometry data measured, know the active pressure and the different radial and the different traces. This was done by Rusbamini, is one of the other postdocs. He's at University of Akron. And this was done in 2002, and this is a paid political announcement, but I always tell Rusbam that paper gets more citations than everything he did with his mentor, Victor Barokins. He had them all up. Only because Victor and I are very good friends, but we have a little friendly rivalry as to which one has more citations. Anyway, that's not important. What is important is that we can take this and map that same model. And this paper just came out in BMNB, and we actually saw what happens when you put a valve ring on. And what does that valve ring do? Well, in the center part of the leaflet, it reduces not the circumferential, but the radial strains are profoundly reduced. Go back to the downscale model of what's going on in the leaflet. We found that the nuclear aspect ratio gets pushed way down from about 5 to about 3.5. And we think that that has a lot to do with the fact that what happens after surgery is the opposite of what happens during dilation, is that this actually causes the valve to be understimulated in antiplastic ring. And then when we look at that, we did a study that just came out in JRSI where we looked at this is based on in vitro data, but we were able to map, again, once you have these modeling techniques, you can map things from vitro to vivo fairly easily. And then we said what happens is that we found that this range, this green range, about 2 to 5, is about what we think is physiologic. When you load the tissue beyond that, it becomes hyperphysiologic and everything gets upregulated. And if you go hyperphysiologic, things get profoundly downregulated. So you not only do you have to keep it in to be happy, if you overstretch it, you make it hypersynthetic, and it's also deleterious if you understretch it. Understretching doesn't mean it's shielded, it actually will, the tissue will actually become necrotic and fail. Okay, so where are we going with all this shit? We're working on what everybody else does, which means to write the next grant. But seriously, what we're doing now is using this to guideline to optimal repair procedures, because all these repairs are one size fits all. It's a very simple ring, and we said we got to do a lot better than that. And it turns out that there's all kinds of problems with that, depending on the nature of the infarct. Certain infarct patterns tolerate the ring very well, patients with that. Others very poorly, but all the surgeons do the same thing for all patients. And what we're doing now is to discriminate between those where some candidates may be better for replacement, some for repair, and those you repair want to be able to have a patient-specific ring or what's called augmentation. Augmentation simply means they took patches of repair material, augment the valve. And patients that, if that's done properly, can have many years of successful repair. So this is kind of where we're going on the practical side. And on the more long-term modeling side, we've developed in parallel all this mitral valve shit. A complete biventricular model of the heart that includes a compressibility, and I talked to some people about that already. I don't have time to talk about that now. What we're doing now is we're taking the mitral valve model and using those techniques to insert the mitral valve into the left ventricle, combine it with infarction, and look at surgical procedures, for example, external patches and so on, that can be used to augment and prevent the ill effects. So the idea is that you really have to look at this as a holistic approach. You have to look at the whole ventricle, because the valve is just one small part of it, even though it's very complicated. Now, as I tell everybody, I don't actually do any of this work. I just talk about it and write sign purchase orders. Andrew Dodson did mitral valve, and Amir did all that beautiful geometry work. Sama did all the mechanology work. Bruno's done much of the 3D reconstruction, showing how it did the first initial models, and even after doing that, he's still smiling. There's our generous foundation support, NIH, American Heart, great collaboration with the Gorman Research Group at Penn, Yogi Nathan. We've all been working together for much longer than any of us want to admit. So that's good. There's the whole group there a couple years ago with the stairwell still standing. And if you want to learn more about this, we have this really great website. We just got our name changed to the Williston Center for Computational Modeling and Simulation. One thing nice about living in Texas, there's a lot of crazy billionaires out there who throw money at all kinds of insane things like our lab, and so that's turned it out. So thank you very much.
Any question for Dr. Seth? Any
5 minutes
question?
early. Yeah.
Did the Chordae remodeling get longer?
Nobody knows. As far as we know, we've never been able to make that measurement because we have no way of knowing what it is beforehand. That's the problem. So the leaflets, you can measure them before, and there's so much variation of that there. It's hard to come up with that clean. So the way we get around that is that calibrated Chordae system that we just try to figure out what they are. Generally speaking, they're as far as we know, they're fairly inert. The only time you have problems with them is when for those people who have myxomatous valve disease, and sometimes you'll get a portal rupture, but that's not too often.
How do you, I'm wondering about that remodeling that you mentioned, about the valve and at the figure level, how we can picture that. You mentioned that probably the cells synthesize more collagen, which make the collagen fibers more crimped again. How would that work with the squeezing those monomers in between the existing one? It seems difficult for me to imagine how that should work.
I'm not sure what the question.
So you had
there were several questions in there. Which one?
You had this result where the mechanics changed of the valve.
Yeah.
It would shift back and forth in pregnancy.
Yes.
And it was involved with the change in crimp. First the crimp was
So how does it do that?
And then the crimp comes back.
Nobody knows.
And you mentioned it.
Nobody knows. It's unknown exactly how that process happens.
Because that has been seen in other tissues and it really.
Yeah, so there's a question of, is it replacing fibrillar units, like collagen units in place? Is it probably, I suspect, just from intuition, it's more at the fibrillar level.
Yes, I think
so it's placing those. So, but what's happening is that the overall structure of that valve is maintained, but what it's effectively doing is lengthening the fibers out. But it's lengthening them in a very peculiar way, so the net compliance stays the same, but there's a shift in the structure. And what's interesting is that I think what really got us interesting here is it's an unknown but not arbitrary process. Okay, and if you go back to this is what really got me interested in, because we went back to this part. Pass over the stick here. Okay, this. So this level is the same as the number. So they want, and everything based on that other paper, but they want to be in the certain strain range. So all they can really do is to modify the exo matrix to return it back to that range that they like to be in. So unlike other tissues, this also tells you a very limited ability to recover back to what you have. You can never completely recover it back. The one thing we don't know is what the valve looks like after pregnancy. After the second, this was just a single pregnancy shock. Yeah.
So for your patient subject basic model, how you determine the actual property for your consulate patients? So you talk about the patient subjects basic cognitive model, right? You want to that.
That's right.
So then you have consulate patient. Then how do you decide this material property from the patient subjects?
Yeah. So how do you do that? Yeah, that's an excellent question. And the way we get that out now is remember the original idea I mentioned is you come up with this sort of atlas, and we found that for a patient, and we just sort of morphed the atlas to that one. We actually found we don't need to do that. What you can do is you can reconstruct the valve leaflets in the opened and closed states, and then through a procedure that I didn't have time to get into, elaborate too much today, we can calibrate and the mechanical properties for that valve. So we know the pressure loading, we know the geometry, we know the boundary conditions, we know what the mechanical properties have to be for that to happen. And so we actually determine the specific mechanical properties of that valve for that patient on an individual basis, based on that inverse fitting process.
Inverse fitting, okay.
That's basically how we get it out. And that solves a wide range of problems, because not only in the normal valve there's a great deal of variation, but in all these infarcted valves there's a lot of variation. If you're dealing with, one of the other big problems is in mitral valve prolapse is called the myxomatous valve, where the valve is actually, it's a degenerative disease of the connective tissue itself. And it's not well studied because nobody really has any way of getting at the physical properties of the human valve. It doesn't seem, there's some dog models of this, but they're not very good. So what we're trying to, so by doing this, we can actually find out what the properties of that are. So we're thinking of extending this also to the myxomatous valve patient.
Yeah, I have another question. So when you talk about your multi-scale model, so you also talk about cellular deformation and a certain cellular deformation, right? And certain
Yes, right.
deformation. So in your multi-scale model, you will incorporate the cellular deformation into in your contour equation, or you have to deal with multi-scale?
Well, the multi-scale is necessary. We haven't, this has only been done in the ovine prep. We haven't done this for humans because there's not, it's difficult getting tissue. It's like that old Monty Python movie joke, you know, can I use your heart? No, I'm sorry, I'm still using it. So we have kind of a major problems with that, although there are sources of human hearts that we found that you can actually purchase. They're not that expensive, and so we're going to use a look, but they're dead. I mean, we can use them for geometry studies, but not for living tissue studies. So part of the way we hope to get around that problem is by using these inverse methods to get out and see how the valve changes. So we actually eventually, like even the pregnancy study, we like to go back, and if we can get 3D ultrasound of human mothers during pregnancy and get that out. This is a totally open-ended field. Nobody's ever really studied how valvular tissues remodel under altered stress, because basically what surgeons have always done is you just repair it or replace it. They don't really think too much about it. But it's extremely important if you're down the road, you're trying to develop so-called engineered tissue valves or other ways to use a regenerative medicine approaches, which I think is where the field needs to go, to get out these issues, to find out how the native valve actually works. So there isn't, basically this is the first time anybody's actually documented an ability for the mitral valve, any valve tissue, to remodel under purely altered physical loading conditions. It's a completely non-pathological process. But, well, I shouldn't say that. I mean, there is relaxin being submitted in the system, but we don't know if there's relaxin receptors in the valve interstitial zone.
Okay.
That's it.
Okay. Any other?
So Michael, it seems very exciting. It's kind of machine learning and personalized medicine.
I'm learning, the machines aren't yet.
So it's more of serve the clinic. Do you see the pathway, the research, how will serve in the surgeons in Texas and the entire community will utilize the knowledge of modeling?
Yeah, well, the idea is the best way I can say it is a surgeon, a very well-known surgeon in Boston told me a few years ago, he said that they want to make surgery a science, not a religion. So most of the stuff is just their surgeons are really good at what they can do, but you know, when it comes to patient-specific models, once you get down to a certain point, there's this huge gap that they don't understand where it goes. And even something as big, like the biggest question that people who do mitral valve surgery is, do we repair or do we replace? And some tolerate the repair very well, but not everybody, and sometimes the repair actually makes it worse in certain types of cases. In that case, they should just have a replacement. Very basic question, and this is the thing that we try to do. So the idea, because otherwise, if the prognosis for a bad mitral valve repair is very, very poor. Within often 6 months, you can have a 2 to 3+ rate of regurgitation. And then also, but the other big thing is getting into the therapy, combining with therapies for the left ventricle, and that's where it integrated in, and that interrelationship between how much the left ventricle can withstand and how much that affects the mitral valve and how much it regurgitates, so it's all unknown. So that's where.
Okay, one more question. Oh, two more.
Yeah. So you're more serious.
Considering other studies on viscoelastic properties and looking at your histology, in ligaments and tendons, we very often see that the set strain in cyclic loading changes depending upon the rate and amount of loading. We also see that the microstructure.
You know what I did? I can answer your question. And I spent about $35,000 and 2 years of a student's life building state-of-the-art biaxial tester.
Yeah.
For the sole purpose of doing high-speed physiological rate tests on valvular tissues.
Yeah.
You know what we found? Doesn't do anything. You can go 3 to 4 increase in order of magnitude in strain rate, and they do exactly the same thing. valvular tissues, to the best of our ability to measure, are strain rate insensitive. They are functionally elastic. So I can take them under certain aphysiological conditions and make them do relax in someone. When you put them in a functional situation like this, nothing happens. They're elastic structures. And that makes perfect sense functionally.
Fantastic.
That's
I would
it.
not have known that's
I-
quite different than the other. This next question, though, in these Chordae, after they're remodeled, after you're talking about something repaired, would you anticipate a different diameter related to structure?
I don't know. The chords are still something that we haven't got a chance to look at. It's because they're not imageable, so we can only look at them afterwards. So we're going to probably need to go back and look at some of those post-implant to see if there's any cord left. So we can take a look. Generally speaking, the chords don't really remodel there. They're so overbuilt. All the remodeling seems to occur in the leaflet to the best of our knowledge.
Thank you. Fantastic lecture.
Thank you.
Okay, we have one more question. Fine.
Are there any other conditions that are similar almost to pregnancy in the sense that it like mimics myocardial infarction, that it goes back after a certain time period that you'd like to like investigate, or?
I don't know. That's a really good question, because that means what happened, to what that begs the question. Certain surgeons have told me that they'll do, a patient will come in with an infarct with a very mild regurg, and they're right on the border whether they put the ring in or not. They do revascularization, coronary bypass, and then it goes away, and then it comes back a little bit, and then it goes away again. So there's this difference where you're just on that bridge of what happens, and there's a lot, and that may be because what's happening, they think, is that the valve is remodeling or stretching out, and therefore we can regurg a little bit, and then it'll recoapt again. And if there's no further change in the ventricle, they're usually okay. But if there is, and then it can change. So there's this dynamic interplay between what the valves are doing and what the ventricle is doing.